In this segment, what we will do is, it's a small segment. Before we get into the derivation of the generalized wave equation, this segment is talking about or deals with the difference between the Eulerian and the Lagrangian viewpoints. Okay, and in a way, this will tell you that when or under what conditions you can neglect something and when you cannot neglect things. Okay, so for that, see, the situation is like this. Suppose you have again we will discuss in case of 1D, and then we will come to because it's now, suppose here we will be talking about the Lagrangian one, and here we will talk about the Eulerian one. Okay. Now, suppose the point is, in fact, in the Eulerian viewpoint, which generally we will go or use, the thing is we don't have even a proper or easy way to define displacement, which we will show, and we will try to visualize them, and we will see how amplitude of oscillation will decide whether we can neglect or we can consider Eulerian and Lagrangian viewpoint to be equal or not equal. Okay. So, that is what we are going to quantify in a way. Okay. Now, so in Lagrangian, what it means is, suppose there is a point here at say the x coordinate being x naught, and after some time this has gone to this point which is the position x, capital X, which will be a function of x naught and t. Okay. So that is the meaning of Lagrangian, saying that the position now we are referring to the particle with respect to its original position, okay, and time, as opposed to in Eulerian we are saying that x is x and t. Okay. That means, so at the same location, okay, we are not referring to the particle with respect to its original position, but with its current location. Okay. So the advantage of this view is, you can straight away say that, means if d rho by dt in Lagrangian so is actually the change of density with respect to time. Means if it is negative, you can say that density is reducing of a particular volume of fluid, and we will always use the total derivative symbol d for Lagrangian and the partial symbol for the Eulerian. Okay. So if you look at this picture, so here we are saying that the displacement of the x naught particle is like, capital X minus x naught. Okay. And suppose we take the displacement function or the position function to be like this, suppose say x naught plus a sine omega t minus k x naught. Okay. Suppose this is what we have taken to be the displacement function in Lagrangian. So please note that all these things are x naughts. So this tells you that, and you can also imagine that every particle here, so they are named with their positions at t equal to 0. Means when I am writing x naught, you are actually talking about the particle whose name is x naught. Okay. So that means this is a function of the name of the particle, which is also the original location where it was when we started everything. okay, and then at time where that particle is. So this equation is telling what is the position of the particle whose name is x naught at any time t. Okay. Now, but then what is this? Means x, if you are sitting here at a location x and talking about the displacement, then what exactly you are asking is at different times different named particles will come to this location, okay, and you are looking for whatever is their displacement. For example, you can say that x of x naught t, suppose this is equal to x. Now whatever x naught, okay, whatever is the name of that particle for whom this happens to be the solution, or the case, this happens to be the case, then for that particle whatever is the displacement, means from this equation you should calculate what is x naught, and then you should substitute that here in this to get the displacement of that particular time, and that is the Eulerian displacement in a way. Okay, that means it's a two-step answering process, that if you ask what is the displacement at a particular time at x, you have to first ask this question, who is the person who is there at x at time t. So once you answer this question, you substitute this and ask what is the displacement of that particular person. So that will be the displacement. And now how to get that? So for that, first I will just show you graphically what it means. Now, so this is the curve, many curves for many particles which have been drawn. The same displacement function has been plotted here. This side is time, this side is their locations, okay, on that tube. Now, what every curve, each of these curves tell you is, suppose this green one, yeah, at 0 it is 0. So that means it is telling you that the particle whose name is 0, because we are naming the particle with their coordinates when they were at 0. So the 0 particle, its motion with time is given by this green one. Okay. Now here I have named as if means this next one is like -1 particle, this side. So -1, now I am referring -1 as a name, okay. -1 is moving like this with respect to time. -2 is moving with respect to time like this. And see this this slope of the peaks, so that is coming because the wave is propagating, isn't it? If you remember the equation was a sine of omega t minus k x naught. So like that means the wave is propagating with respect to time. So this slope in a way, not the slope, the inverse, dx over dt, because this side is dx and this is dt. So dx over dt.
There is a delay in the peak.
There is a delay in the peak, and that is coming because finite speed of the motion. So now suppose you are sitting at say 2. Suppose small x is equal to 2 is your Eulerian position where you are sitting and trying to see the displacements. So what do you mean by the displacement of a particle at small x is? See and then you have to talk about time. Here in the picture at this time, suppose whatever is that thing, okay, this location, this point, the time will be somewhat like 1 second, suppose. Okay, that means, and this curve is say 1, 2, 3. So the 3 particle, so particle whose name is 3, it is at 2 at 1 second time. Okay, that means if you are sitting at the location x is equal to 2, that means particle 3 is at that, and its displacement, whatever is the displacement of that particle, will be the displacement which you are talking about, Eulerian displacement. Similarly, the velocity is the slopes of these curves of different particles at different times. So suppose you are sitting at 2, so at 1 second the slope of, or negative, whatever you understand what I mean, dx by dt, this means run by rise, generally the slope is rise by run. So here we are talking that whenever I am telling slope, I mean the run by rise, okay, not the rise by run. Okay, so that slope for the particle 3 will be at 1 second. Now the next one is a particle 2 is coming at 1.2 second, sort of. That means at 1.2 second the slope of particle 2 is the velocity at x equal to 2, because we are looking at this point. So that means at every location we are at different times, so small x is 2, and at different times we are asking the question which curve we need to follow, and we are looking for the slope, and we are telling that as the velocity. And similarly the acceleration is the rate of change of those slopes over time. So that is the Eulerian way of velocity, displacement and acceleration, okay, thinking in Eulerian way. And then that is why it's so this is the meaning of what you should call as velocity and acceleration from the picture, okay. Now if so what you should think now is, suppose you want to plot the displacement, the way now we define displacement, it's clear, right? Now if you draw that displacement, you will see something like this, curve like this. Obviously it is not a sine curve, right?
So this is the displacement of?
This is the Eulerian displacement of at x, small x is equal to 2, suppose, when at a particular, I think it is at 0, okay. So this curve is at x equal to 0 at the origin. So this is the displacement function, okay. Now this obviously very clearly it's not a sine curve. Now this difference between this and the actual sine, because see, if you remember the other curve which we had just plotted, the Lagrangian displacement is completely sine. You see this green, if you see, it's a sinusoidal one, and okay, so the plot, the function which has been plotted is that a sine omega t minus k x naught at x naught equal to 0 and at different times. So that is the function. So this is completely sinusoid, but the other displacement, Eulerian displacement curve, is not a sinusoid. This is not a sinusoid. And similarly you can plot at any point, it will not be a sinusoid. And similarly the velocity, if you plot, it will not be a cos function either, okay. And that is why, though you are getting an advantage of experimentally seeing things very easily by sitting somewhere, you are getting into this trouble of what? For example, suppose you get the velocity function like this, and if you integrate it, you won't get this. because its derivative is not that velocity.
Eulerian velocity is.
So it is the Eulerian displacement, you can say.
Okay, that is.
Now its derivative is not the velocity which you are seeing at as Eulerian velocity. So that is why you can't integrate Eulerian velocity to get Eulerian displacement. Similarly, you cannot just integrate Eulerian acceleration to get Eulerian velocity. So that is, and then these statements which I am making now, they are true when the amplitude is high. Now if I decrease the amplitude of the waves which I have plotted now, you will see that these curves will be more and more like the sines and cosines. This curve will be very much like sine if I increase the amplitude. I have taken a very high amplitude of oscillation. This I am talking about this amplitude. If I decrease this, you will you can see that that curve will become more and more like the sine.
So you mean to say that the particles that you are considering are spaced apart, like considerably?
No, I am talking about the A which
Each particle is high.
each particle's amplitude. So that's I am talking about. So if I decrease that, I'll try once to run that maybe by decreasing. So this is that A, okay, which I am talking about. Say if I take say 0.1. So are the curves coming because I'll okay, see that now the amplitude has reduced, the new curve, and what happened to the other one? Is it visible? Yeah, you see this, the red one. So that becomes almost like a sine curve. Okay, so this tells you that pictorially, still we haven't discussed anything in equations. Even we didn't discuss how to get this from equation, but the thing is, the amplitude of the motions is telling you that whether you can what terms you can neglect from converting from Eulerian to Lagrangian, Lagrangian to Eulerian, because Lagrangian view is the view which actually is happening, and Eulerian is the view which you have in a way accepted that I'll use this because it is easy to get experimentally. But then if you want to use those data for your further prediction, calculations and all those things, you must know how to correct it to get the Lagrangian one, and you should also know whether I need this correction depending on the amplitude at which you are talking about. So that's the point of discussion of this segment.
You are telling that Eulerian one is easier to get experimentally.
Yes, yeah, because you are sitting at a location, you are not moving with that, right? Because if you if you consider say the Lagrangian one picture, here to get the displacement of say different particles, you will have to sit on different particles and move along with those curves, different curves, and it's difficult to do experimentally.
But then displacement, how do you find, like, you don't know where the particle has started also, right?
So that's the thing. So for this one we now discussed at least qualitatively, right? And in fact I can even qualitatively tell how to get it. For example, from the curve which you saw, the displacement curves, okay, those set of these shifted curves, you know. From these curves, you can actually plot the displacement field from looking at these pictures. Even if you don't derive an equation for getting the displacement field, you can actually get from these Eulerian, Lagrangian curves.
We can convert.
Yeah, you can always do that, right? Because you sit here, you see what say first you have to look for at what location you are trying to plot that next curve. As I said, the other curve of displacement was plotted for x is equal to 0, right? I said that this curve of displacement has been plotted for x is equal to 0. So, first you have to fix that at what location you are trying to find out the displacement field. Okay. Now, once suppose you fix that, at say 2 or whatever, 1 or 2, let us say 2 or 1, let us say 1. Okay. You fix that at 1, I want to draw the displacement field. Then what you need to do is you have to then move from time to time. Okay, at every time, say at 0.1 second, you have to look for which particle curve, you have to draw a lot of them curves, and you have to see at t equal to 0.1 which particle is crossing, and just plot that x naught difference of x minus x naught, you plot that against that time. Similarly, at 0.2, if you say, you look for which curve is crossing at 0.2 time, and its name you plot it there, x minus x naught plot against that time. So, if you keep on doing that for different times, you will get a curve for x is equal to 1 at various times. So, that is how you can do experimentally also in a way which is very impractical. And then that is why the point of this discussion is that you should understand the origin of the difference between these two, and why one is and in which situation one is better than the other, because this view is very easy to evaluate experimentally, but then that is the actual thing which is happening. If you want to use Newton's law, force is equal to mass times acceleration, you have to apply on this, because this is a very perceived acceleration, because at every time the particle is changing. So, you can't apply the directly F equal to ma on that, because the next instant you are talking about next particle, another particle. Okay. So that is why first you should understand the difference, and then you should understand this difference is significant when the amplitude of the velocities are more, and that will give you an idea when and where you can neglect the difference between these two viewpoints and where you cannot. Okay. Now coming to say, okay, I will stop the video because and then again I will start it to tell about how to get this quantitatively, because till now we discussed qualitatively. Okay. See you in the next segment.